Right now, somewhere in our galaxy, a massive star is shining peacefully. Its surface looks calm. Its light is steady. Nothing about its appearance suggests anything is wrong, but deep inside, buried beneath trillions of tons of stellar material, something has just gone catastrophically wrong. The core of this star has begun to collapse, and once it starts, nothing in the universe can stop it. In less than 1 second, the inner core will be crushed from a region the size of Earth down to a ball roughly the width of a city. Temperatures will spike to over 100 billion degrees. More energy will be released in neutrinos alone than the sun will produce in its entire 10 billion year lifetime. All of it in under 1 second. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Imagine a star sitting out in some distant arm of our galaxy, 20 times more massive than our sun. If you pointed a telescope at it tonight, you would see nothing unusual. Its light would be steady. Its color would look exactly the way it has looked for millions of years. The surface, a churning ocean of superheated plasma, would show no sign of distress, no dimming, no flickering, no visible warning of any kind. And yet, deep inside this star, hidden beneath trillions upon trillions of tons of stellar material, something has already gone wrong. The core of this star is dying. Not in the slow, gradual way that our sun will eventually fade, but in a sudden, violent way that cannot be reversed, cannot be slowed down, and cannot be survived. Within the next few hours, the conditions inside this core will reach a breaking point, and when they do, the collapse that follows will unfold so fast that it will be essentially finished before the surface of the star has any chance to respond. That is the fundamental strangeness of what happens in the final moments before a core collapse supernova. The outside of the star has no idea what the inside is doing. Light from the core cannot reach the surface quickly enough. Sound waves cannot travel fast enough through the dense layers above. The information about the catastrophe unfolding at the center is trapped, sealed behind an almost unimaginable wall of matter. By the time the surface finally reacts, by the time the star visibly changes, the collapse will already be over. The core will have been crushed. A neutron star or a black hole will have formed. And a shock wave carrying more energy than you can reasonably comprehend will be tearing through the star's outer layers at tens of thousands of kilometers per second. But all of that comes later. For now, we need to understand how a star arrives at this moment. How does a perfectly normal, brilliantly shining star build something so dangerous at its center that the whole structure tears itself apart? The answer lies in how stars generate energy, and it begins with something you already know about: fusion. Stars exist because of a constant battle between two forces. Gravity pulls everything inward, trying to crush the star down to the smallest possible point. And the energy generated by nuclear fusion in the core pushes outward, creating pressure that resists that inward pull. As long as these two forces are in balance, the star is stable. It shines, it holds its shape. It can endure for millions or even billions of years. Our sun has been maintaining this balance for about 4.5 billion years, and it will continue doing so for roughly another 5 billion. It fuses hydrogen into helium in its core, and the energy released by that process creates enough outward pressure to keep gravity from winning. The sun is a simple star in this regard. It has one fuel source, hydrogen, and it burns through that fuel slowly, steadily, reliably. It will never do anything more dramatic than swell into a red giant and eventually shed its outer layers, leaving behind a cooling white dwarf. That is the fate of ordinary stars. But the star we are talking about tonight is not ordinary. A star 20 times the mass of the Sun lives a fundamentally different life. It burns hotter, it burns faster, and most importantly, it does not stop at hydrogen. It keeps going, fusing heavier and heavier elements, climbing up the periodic table in a desperate race to keep generating enough energy to hold itself together against the relentless pull of its own gravity. And that race will eventually reach a dead end. An element that cannot be burned. A fuel that is not fuel at all. Let us walk through what happens inside a massive star from the very beginning. When a massive star first ignites, it does the same thing our Sun does. It fuses hydrogen into helium. In the core, where temperatures reach around 15 million degrees and the pressure is enormous, hydrogen nuclei are forced close enough together that the strong nuclear force can bind them. 4 hydrogen nuclei combine through a series of steps to produce 1 helium nucleus. But here is something subtle and important. When you weigh the helium nucleus that comes out of this reaction, it weighs slightly less than the 4 hydrogen nuclei that went in. A tiny amount of mass has vanished. That missing mass has been converted into energy according to Einstein's famous relationship between mass and energy. And even though the amount of mass lost in a single fusion reaction is incredibly small, the number of reactions happening every single second is so enormous that the total energy produced is staggering. Our Sun converts roughly 600 million tons of hydrogen into helium every single second. About 4 million tons of that mass is converted directly into energy every second. That is what keeps the Sun shining. Now, a star with 20 times the mass of the Sun does this same process, but on a vastly larger scale. Its core is hotter, denser, and under much greater pressure. This means the fusion reactions happen much faster. Where the Sun will burn through its hydrogen over roughly 10 billion years, a massive star might exhaust its core hydrogen supply in as little as 8 to 10 million years. That sounds like a long time by human standards, but on cosmic timescales, it is remarkably brief. The Sun has been alive for nearly half the current age of the universe. A massive star lives for less than 0.1% of that time. It is burning through its fuel at an almost reckless pace, and the consequences of that pace will become apparent soon enough. In the Sun, hydrogen fusion primarily happens through what is called the proton-proton chain, a relatively simple sequence of reactions. In a more massive star, the dominant process is different. It is called the CNO cycle, where carbon, nitrogen, and oxygen nuclei act as catalysts, helping to fuse hydrogen into helium more efficiently at higher temperatures. The end result is the same. 4 hydrogen nuclei become 1 helium nucleus, and energy is released. But the CNO cycle runs much faster at the temperatures found in massive stellar cores, which is part of why these stars burn through their hydrogen so quickly. When the hydrogen in the core runs out, the star faces its first crisis. Fusion stops. The outward pressure that had been holding gravity at bay drops, and gravity, which has been waiting patiently for millions of years, immediately begins to win. The core contracts. As it contracts, it gets hotter and denser. And this is where a massive star takes a path that our sun will never follow. The temperatures and pressures become high enough to ignite a new fuel. Helium. Helium fusion is fundamentally different from hydrogen fusion. It requires much higher temperatures, roughly 200 million degrees, compared to the 15 million needed for hydrogen. The process is called the triple alpha process because it involves combining 3 helium-4 nuclei, which are also called alpha particles, to form a single carbon-12 nucleus. This reaction is harder to achieve because it requires 3 particles to come together in essentially the right configuration at the right time. It is less efficient than hydrogen burning and releases less energy per reaction, but it works. For a while. In a massive star, the helium burning phase lasts a much shorter time than the hydrogen burning phase. Where hydrogen lasted perhaps 8 to 10 million years, helium burning might last only about 500,000 to a million years. Already, the pattern is becoming clear. Each new fuel burns faster than the last. Each stage of fusion is shorter than the one before. The star is accelerating towards something, though from the outside, you would never know it. The surface of the star continues to shine as it always has. The drama is entirely internal. When the helium in the core runs out, gravity squeezes the core again. The temperature rises further, and now something new ignites. Carbon, the product of helium fusion, becomes the next fuel. Carbon nuclei fuse together to produce elements like neon, sodium, and magnesium. This stage requires temperatures of roughly 600 million degrees. It produces less energy than helium burning did, and it lasts an even shorter time. In a star of 20 solar masses, carbon burning might last only about 1,000 years. 1,000 years. The star burned hydrogen for millions of years. It burned helium for hundreds of thousands. Now it is burning carbon for barely a millennium. And we are nowhere near done. After carbon comes neon burning. At temperatures approaching 1.5 billion degrees, neon nuclei are broken apart and reassembled into oxygen and magnesium. This stage is peculiar because it begins with a destruction reaction. Photons in the core are so energetic that they can actually shatter neon nuclei, a process called photodisintegration. The fragments are then recombined to form heavier elements. Neon burning lasts only about a year, but perhaps less. The core is now racing through its fuel supply at a pace that would be terrifying if anyone could see it happening. Next comes oxygen burning. At temperatures around 2 billion degrees, oxygen nuclei fuse together to produce silicon, sulfur, phosphorus, and other intermediate elements. This stage lasts roughly 6 months, half a year. The star spent millions of years on hydrogen, hundreds of thousands on helium, 1,000 on carbon, a year on neon, and now just 6 months on oxygen. Each step is shorter, each step is more desperate, and each step produces less energy per reaction than the one before it. Let me put this progression in perspective because the acceleration is truly extraordinary. If you scaled the entire life of this star to a single calendar year, with January 1st representing its birth, and December 31st representing the moment of collapse, hydrogen burning would occupy everything from January through roughly the 3rd week of December. Helium burning would take up the last week or so of December. Carbon burning would fit into the last few hours of December 31st. Neon burning would occupy roughly the final 3 seconds. Oxygen burning would take up barely more than one of those seconds. And the final stage, the one we are about to discuss, would flash past in a few thousandths of a second. That is how dramatically the timescales compress, the star spends most of its life on its first fuel and races through everything else in what amounts to the blink of a cosmic eye. The final act of nuclear fusion in the core of this star is silicon burning. At temperatures above 3 billion degrees, silicon-28 and other intermediate nuclei are rearranged through a complex web of reactions into the elements of the iron group. This is not a simple fusion reaction like hydrogen or helium burning. It is a chaotic, rapid process called nuclear statistical equilibrium, where nuclei are constantly being built up and torn apart by the extreme temperatures, and the net result is a gradual conversion of silicon into iron and its closer neighbors, particularly nickel. The reactions favor these elements because they sit at a very special place on the curve of nuclear binding energy, a concept we need to understand clearly because it is the key to everything that happens next. Silicon burning lasts roughly 1 day, one single day. After millions of years of hydrogen burning, after hundreds of thousands of years of helium, after 1,000 years of carbon, after a year of neon, after 6 months of oxygen, the star burns through its last available fuel in approximately 24 hours. By the time this final day of silicon burning is done, the core has been transformed into a ball of iron and iron group elements, roughly the size of Earth. And with that, the star has reached the end of the line. To understand why iron is the end of the line, you need to understand binding energy. This is one of the most important concepts in nuclear physics, and it explains everything about why stars can burn some elements but not others. When protons and neutrons come together to form a nucleus, the resulting nucleus weighs slightly less than the sum of its individual parts. The missing mass has been released as energy, the energy that binds the nucleus together. This is the binding energy of the nucleus. The more tightly bound a nucleus is, the more energy was released when it formed, and the more stable it is. Different elements have different amounts of binding energy per nucleon, meaning different amounts of binding energy for each proton or neutron in the nucleus. If you plot binding energy per nucleon against the number of nucleons in the nucleus, you get a curve. This curve starts low for the lightest elements, rises steeply through helium, carbon, and oxygen, and reaches a peak right around iron. After iron, the curve slowly declines as you move to heavier elements. This curve is the reason fusion works at all. When you fuse two light nuclei together to form a heavier one, you are moving up the curve. The product nucleus is more tightly bound than the original nuclei were. The difference in binding energy is released as energy. That is the energy the star uses to shine. Every step of the fusion chain, from hydrogen to helium, from helium to carbon, from carbon all the way through to iron, involves moving up this curve toward higher binding energy per nucleon and releasing the difference as useful energy. But iron sits at the peak. There's nowhere left to go. If you try to fuse two iron nuclei together, the product would have less binding energy per nucleon, not more. You would have to put energy in to make the reaction happen. Instead of releasing energy, the reaction would consume it. It would absorb energy from its surroundings. Instead of supporting the star against gravity, it would actually steal thermal energy from the core, making the problem worse. This is the fundamental reason that iron is a dead end. It is not that iron cannot undergo fusion. Under extreme enough conditions, iron nuclei can be forced together. But the reaction takes energy from the environment instead of adding to it. It is an endothermic reaction, and a star cannot survive on endothermic reactions. That would be like trying to heat your house by running the air conditioner. The more you do it, the colder it gets. Let me emphasize this because it is genuinely one of the most important facts in astrophysics. The binding energy per nucleon curve dictates the life and death of every massive star in the universe. Light elements can fuse and release energy. Heavy elements can split apart through fission and release energy. But iron and its neighbors sit at the summit. They are the most stable nuclei in nature. You cannot extract useful nuclear energy from iron by any process, neither fusion nor fission. It is the ultimate nuclear ash, the end product of the most efficient energy extraction process the universe allows. Think of it this way. A fireplace burns wood and produces ash. The ash is the leftover material that cannot burn anymore. No matter how hot you make the fire, the ash just sits there. It has already given up all the chemical energy it had to give. Iron is the nuclear equivalent of that ash. It is what remains when a star has extracted every last bit of nuclear energy that physics permits. It is spent fuel, dead weight, and now it is accumulating at the center of this star with nothing to stop it from piling up. This is the situation the star finds itself in during its final day. Silicon is burning furiously in a shell around the core, and the products of that burning iron and iron group elements are raining down onto the core like snow settling on the ground. The core grows heavier and heavier with every passing hour, but none of that iron can be used for fuel. It simply accumulates. A growing ball of useless ash at the center of the star, supported not by the energy of fusion, because no fusion is occurring there anymore, but by something else entirely. Electron degeneracy pressure. To understand electron degeneracy pressure, we need to take a brief detour into quantum mechanics. In quantum physics, there is a rule called the Pauli exclusion principle. No two identical fermions, particles like electrons, protons, or neutrons, can occupy the same quantum state at the same time. Electrons are fermions, and this rule applies to them absolutely. You cannot force two electrons into the same quantum state. It is not a suggestion. It is a law of nature as rigid as any we have ever discovered. When matter is compressed to extreme densities, the electrons inside it are squeezed into smaller and smaller volumes. As the available space shrinks, the electrons are forced into higher and higher energy states because the low energy states are already occupied. They cannot all be in the lowest energy state because the Pauli exclusion principle forbids it. So they stack up, filling energy levels from the bottom to the top, each electron occupying its own unique state. This creates a pressure, a resistance to further compression that has nothing to do with temperature. Even if you could somehow cool the material to absolute zero, this pressure would remain. It is a purely quantum mechanical effect. It is what prevents a white dwarf star from collapsing further under its own gravity. And in the iron core of a massive star, electron degeneracy pressure is doing the same job. It is the last remaining force holding the core up against the crushing weight of the entire star, pressing down on top of it. But electron degeneracy pressure has a limit. It can only support so much weight. And that limit was calculated in 1930 by a brilliant young Indian astrophysicist named Subrahmanyan Chandrasekhar, who was only 19 years old at the time, travelling by ship from India to England to begin his graduate studies at Cambridge. During that voyage, working with the mathematics of quantum mechanics and special relativity, he realized something that would shake the foundations of stellar physics. There is a maximum mass that electron degeneracy pressure can support. If a stellar core exceeds this mass, no amount of electron pressure can prevent its collapse. This critical threshold is now called the Chandrasekhar limit, and its value is roughly 1.4 times the mass of our Sun. That might sound like a lot of mass, but remember, we're talking about the core of a star that is 20 times more massive than the Sun. The whole star weighs far more than 1.4 solar masses. The question is whether the iron core alone can stay below that limit. The answer is that it cannot. Not forever. Silicon burning keeps adding iron to the core. With every passing hour, the core gets heavier. It creeps closer and closer to the Chandrasekhar limit, and the conditions inside the core are making things worse in ways that go beyond simply adding mass. The core is incredibly hot, with temperatures exceeding 5 billion degrees. At these temperatures, the electrons in the core are moving at speeds that approach the speed of light. They become what physicists call relativistic, and relativistic electrons provide less resistance to compression than non-relativistic electrons do. The degeneracy pressure weakens at exactly the moment the core needs it most. This is a crucial point that often gets overlooked. The Chandrasekhar limit is not simply a matter of piling on more mass until something breaks. The physics of the electrons themselves changes as conditions become more extreme. The faster the electrons move, the less effective they are at providing pressure support. And in the iron core of a massive star, the electrons are moving at nearly the speed of light. The support they provide is already diminished. The core is already closer to the edge of stability than a simple mass calculation would suggest. If you could slice the star open right now and look at its interior, you would see something that resembles the layers of an onion. At the very center is the iron core, a dense ball roughly the size of Earth, but containing more than a solar mass of material. Surrounding this core is a thin shell where silicon is actively burning, producing the iron that feeds the core's relentless growth. Outside the silicon burning shell is a layer of oxygen and neon. Beyond that, a shell of carbon, then a layer of helium. And finally, the vast hydrogen envelope, the outermost layer, extending millions of kilometers into space. This is the part you see when you look at the star through a telescope. Each layer is the product of a previous stage of fusion. Each one was once the core fuel, and each has been left behind as the core moved on to burning heavier elements. It is like a geological record of the star's entire nuclear history, with the oldest fuel on the outside and the newest product at the center. And right now, the innermost layer, the iron core, is the only one that matters, because the iron core is the one approaching catastrophe. The outer layers of the star are almost completely unaware of what is happening at the center. The hydrogen envelope, that vast, luminous outer shell, is still behaving as though nothing is wrong. It takes time for information to travel through a star. A sound wave in the star's interior might travel at a few hundred kilometers per second, but the star is millions of kilometers across. By the time any signal from the core could reach the surface, the collapse will already be over. The surface of the star is living in the past, displaying conditions that reflect what was happening at the core hours or days ago, not what is happening right now. Right now, the core is on the edge of something irreversible. The iron core has grown to nearly 1.4 solar masses. Electron degeneracy pressure, weakened by the relativistic speeds of the electrons, is barely holding the core together. And the situation is about to get dramatically worse, because two processes are about to begin that will strip away even this last line of defense. These two processes acting together, will destroy the core's ability to support itself in less than a single second. But we will get to those soon. For now, consider the state of this star. From the outside, it looks like any other bright, massive star. If you had been watching it for your entire life, you would have seen no change. If your grandparents had been watching it for their entire lives, they would have seen no change either. The stars looked essentially the same for millions of years. It has been a steady, reliable point of light in someone's night sky for as long as complex life has existed on any planet orbiting nearby stars. But on the inside, this star has been secretly racing toward its own destruction. It burned through hydrogen for millions of years, then helium for hundreds of thousands, then carbon for 1,000 years, then neon for a year, then oxygen for 6 months, and then silicon for a single day. Each stage faster than the last, each stage more desperate, each stage producing less energy than the one before. And now, with an iron core sitting at the center like a ticking clock, the star has reached the final stage. The one that happens not in millions of years, not in thousands, not in months or days, but in a fraction of a single second. The iron core is balanced on a knife's edge. Gravity is pulling inward. Electron degeneracy pressure is pushing outward. But the balance is failing. The core is too hot. The electrons are too fast. The mass is too great. Something is about to give. And when it does, the collapse will happen so quickly that it will be essentially instantaneous by human standards. Think about what has been built here. Millions of years of steady nuclear burning have constructed this object, layer by layer, element by element, like a tower being built one brick at a time. Hydrogen became helium. Helium became carbon and oxygen. Carbon became neon and magnesium. Oxygen became silicon and sulfur. Silicon became iron. Each transformation released energy that kept the star alive for a little while longer. But each transformation also moved the star one step closer to this moment. The moment when there is nothing left to burn. The iron core is not going to ignite. It cannot ignite. There is no nuclear reaction that can extract energy from iron under any conditions. The star has climbed the entire curve of binding energy from hydrogen at the bottom to iron at the top. And there is no higher ground to reach. For the first time in millions of years, the core has no defense against gravity. It has been producing energy through fusion since the moment it was born, and now, for the first time, it cannot produce anymore. Gravity does not care. Gravity does not pause. Gravity does not wait for the star to find a solution. Gravity has been pulling inward since the moment this star formed from a collapsing cloud of gas, and it has been held at bay only by the energy of fusion. Now that energy is gone, and gravity is about to win in the most violent way imaginable. The temperature at the center of the core is now climbing past 10 billion degrees. The density is reaching staggering values, hundreds of millions of times the density of water. The electrons are screaming through the core at nearly the speed of light, providing what little support they can, but it is not enough. The conditions are ripe for something catastrophic. Two processes are about to begin simultaneously, each one feeding the other in a vicious cycle that will tear the core apart from the inside. But before we describe what those two processes are, stop and appreciate the strangeness of this situation. Right now, at this very instant, somewhere in our galaxy, there is almost certainly a star in exactly this condition. A star that looks perfectly normal from the outside. A star whose light is steady, whose color is unremarkable, whose position in the sky has not changed noticeably in all of recorded human history. But deep inside, its iron core is balanced on the razor edge of collapse. It might hold for another 1,000 years. It might hold for another century. It might hold for another day. Or the collapse might have already begun, and the light carrying that information simply has not reached us yet. We cannot tell by looking. That is the unsettling truth about these stars. They keep their secrets until the very end. The surface reveals nothing. The light tells no tales. And then, in less than a single second, the core falls. Everything changes, and one of the most powerful events in the known universe begins to unfold. The iron core has been built. The fuel has been spent. The last line of pressure support is failing. What happens next will happen faster than the blink of an eye, and it will release more energy than the human mind can reasonably hold. The core is ready to fall. The iron core is now sitting at the center of the star, like a bomb with the fuse already lit. It has a mass approaching 1.4 times the mass of our Sun, and it is compressed into a volume roughly the size of Earth. The density at its center is already beyond anything you encounter in everyday experience, roughly 1 billion times the density of water. A single teaspoon of this material would weigh thousands of tons. The temperature is above 10 billion degrees, and the only thing preventing this entire mass from collapsing under its own crushing gravity is the quantum mechanical resistance of electrons. Electron degeneracy pressure, the Pauli exclusion principle manifesting as a physical force, but that force is failing. The electrons in the core are already moving at nearly the speed of light. Their ability to resist further compression is weakening, and the core, which has been slowly gaining mass as silicon burning dumps more iron onto it from the shell above, is creeping closer and closer to the maximum mass that electron pressure can support. What happens next unfolds in less than a single second. Those two processes have names: electron capture and photodisintegration. Each one alone would be devastating. Together they create a catastrophe that cannot be stopped once it begins. Together they will destroy the core's remaining support so completely and so quickly that the collapse will accelerate to a significant fraction of the speed of light. Millions of years of nuclear fusion will be undone in milliseconds, and the core of this star will go from the size of Earth to the size of a small city in less time than it takes your heart to beat once. Let us take these one at a time, because each process on its own is remarkable. But what makes the situation truly catastrophic is the way they work together. Electron capture begins when conditions inside the core become extreme enough that protons start absorbing electrons. Under normal circumstances, protons and electrons coexist peacefully inside atoms. Electrons orbit the nucleus. Protons sit inside it. They are both stable in their respective places. But in the iron core, conditions are far from normal. The density is so extreme and the electrons are moving so fast that something unusual begins to happen. Electrons are forced into such close proximity with protons that the weak nuclear force can mediate a reaction. A proton absorbs an electron and transforms into a neutron, releasing a tiny particle called a neutrino. This reaction is deceptively simple to describe. A proton plus an electron becomes a neutron plus a neutrino. One line. A few words. But the consequences of this reaction for the core of the star are absolutely devastating. Think about what each captured electron means. Every single electron that gets absorbed by a proton is one fewer electron available to provide degeneracy pressure. Remember, electron degeneracy pressure is the only thing holding the core up. It depends entirely on the number of electrons present. Each electron occupies a quantum state, and the collective resistance of all those electrons pushing against each other is what creates the pressure. When you remove an electron through capture, you remove 1 unit of that pressure. You weaken the support structure. You bring the core 1 tiny step closer to collapse. Now, a single electron capture event is negligible. 1 electron out of an unimaginable number makes no measurable difference. But the process does not stop at 1. As the core grows denser and hotter, the rate of electron capture accelerates. More and more protons swallow more and more electrons. Billions upon billions upon billions of electrons are absorbed per second. The electron population in the core is being systematically depleted, and with it, the pressure that those electrons were providing. The floor is being pulled out from under the core, plank by plank, faster and faster. Each electron capture event also produces a neutrino. And here is something remarkable about neutrinos. Under normal conditions, neutrinos are the most ghostly particles in the universe. They interact with matter so weakly that a neutrino can pass through the entire planet Earth without touching a single atom. Trillions of neutrinos from the sun are streamed through your body right now, every single second, and you will never feel them. They are essentially invisible to matter. Under normal conditions, if you had a solid wall of electron light-year thick, most neutrinos would pass straight through it without being stopped. That is how weakly they interact with the physical world. But this ghostly quality is precisely what makes them so dangerous for the core right now. In the early stages of collapse, the core is still transparent to neutrinos. The neutrinos produced by electron capture fly out of the core at nearly the speed of light, escaping into the star and eventually into space. And every neutrino that escapes carries energy with it. It is not just removing an electron and weakening the pressure support. It is also stealing thermal energy from the core. The neutrinos are acting like tiny energy thieves, each one slipping away with a small parcel of the core's heat. And at the rate they are being produced, the total energy loss is significant. The core is losing energy at the exact moment it desperately needs every bit of energy it has to maintain its structure. So electron capture attacks the core in 2 ways at once. It removes the electrons that provide pressure support, and it produces neutrinos that carry away thermal energy. Both effects reduce the core's ability to resist gravity. Both effects push the core closer to collapse, and the more the core contracts, the denser it gets, and the faster electron capture proceeds, which makes it contract even more. It is a positive feedback loop, a runaway process that accelerates as it progresses. Now let us look at the second process, photodisintegration. If electron capture is like pulling the supports out from under a building, photodisintegration is like setting the foundation on fire. At temperatures above roughly 10 billion degrees, the photons inside the core become extraordinarily energetic. These are not the kind of photons you see with your eyes or feel as warmth on your skin. These are gamma-ray photons, the most energetic form of light in the universe, and at the temperatures found in the collapsing iron core, these gamma rays carry enough energy to do something that sounds almost paradoxical. They can break apart atomic nuclei. This is photodisintegration. A gamma-ray photon strikes an iron 56 nucleus and shatters it. The iron nucleus, which contains 26 protons and 30 neutrons bound together by the strong nuclear force, is torn apart into 13 helium-4 nuclei and 4 free neutrons. A nucleus that took millions of years of stellar evolution to build, destroyed in an instant, millions of years of nuclear work, undone by a single photon. But here is the critical detail. This reaction does not release energy. It absorbs it. Breaking an iron nucleus apart requires a tremendous amount of energy. The photon that shatters the nucleus has to provide all the energy needed to overcome the binding force that held the nucleus together. That energy comes from the thermal energy of the core. Every iron nucleus that gets torn apart absorbs energy from its surroundings. It is an endothermic reaction. It consumes heat. Think about what that means. The core is already in a precarious state. It needs all the thermal energy and all the pressure it can get to resist the inward pull of gravity. And now, photodisintegration is devouring that thermal energy at a staggering rate. Every time a gamma-ray photon breaks apart an iron nucleus, the surrounding material gets colder. Not in any way you would notice with a thermometer, because the temperatures are still in the billions of degrees, but colder in the sense that matters. Colder in the sense that the pressure drops. The thermal pressure that was supplementing the failing electron degeneracy pressure is being eaten alive by photodisintegration. And it does not stop with iron. Once the iron nuclei have been broken into helium-4 nuclei, those helium nuclei can themselves be shattered if the temperature is high enough. A helium-4 nucleus can be torn apart into 2 protons and 2 neutrons by an even more energetic photon, and that reaction absorbs even more energy. The core is being systematically dismantled at the nuclear level, and every step of that dismantling steals thermal energy from the environment. There is something deeply tragic about this if you think about it in the right way. This star spent millions of years carefully building those iron nuclei. It started with hydrogen, fused it into helium, fused helium into carbon, then oxygen, then neon, then silicon, and finally iron. Each step required millions or thousands or hundreds of years of sustained nuclear burning. Each step released energy that kept the star alive. And now, in a fraction of a second, photodisintegration is tearing all of that work apart. It is running the entire fusion process in reverse. The star is literally unbuilding itself from the inside out, and paying for the privilege by consuming the last of its thermal energy. Now, here is why the situation becomes truly catastrophic. Electron capture and photodisintegration do not simply occur side by side. They feed each other. They create a vicious cycle that amplifies both processes far beyond what either could do alone. Here's how the cycle works. Electron capture reduces the pressure in the core. With less pressure to resist gravity, the core contracts slightly. As it contracts, it gets denser and hotter. Higher temperatures mean more energetic photons, which means more photodisintegration. More photodisintegration absorbs more thermal energy, which further reduces the pressure. With even less pressure, the core contracts more. Greater contraction means higher density, which increases the rate of electron capture. More electron capture means fewer electrons, less pressure, more contraction. And around it goes. Each process makes the other worse. Electron capture weakens the pressure, causing contraction, which raises the temperature, which drives more photodisintegration. Photodisintegration steals thermal energy, causing contraction, which raises the density, which drives more electron capture. The two processes are locked together in a death spiral, each one feeding the other, accelerating the collapse faster and faster with every passing millisecond. This is why the collapse, once it begins, cannot be stopped. There is no mechanism that could reverse this feedback loop. The star cannot find a new source of energy, cannot create new electrons to replace those being captured, cannot prevent its photons from shattering its iron nuclei. The physics of the situation is absolute. Once the core crosses the threshold where these two processes become self-sustaining, the outcome is determined. The core will collapse. Nothing can prevent it. The onset is shockingly fast. Within roughly 10 milliseconds of the feedback loop becoming fully established, the collapse is well underway. Within a few hundred milliseconds, maybe 300 or so, the entire inner core will have fallen from the size of Earth to a ball perhaps 30 to 40 kilometers across. The velocities involved are staggering. Material in the collapsing core reaches speeds of 70,000 kilometers per second. That is roughly 1/4 of the speed of light. Matter falling inward at 25% of light speed. Imagine that. Imagine trillions upon trillions of tons of matter, all of it formerly part of a stable stellar core, now in complete free fall, accelerating inward at a speed that defies everyday comprehension. From the outside, the star has not changed. Its surface is still calm, its light is still steady, but inside, the core is falling at 1/4 of the speed of light, and it has been doing so for less than a second. During this collapse, the core does not behave as a single uniform object. A critical distinction emerges between two different regions, and understanding this distinction is essential for everything that comes later. The inner part of the core, roughly the innermost 6/10 of a solar mass, collapses in a very specific way. It collapses homologously, which means it falls inward as a coherent unit. Every part of the inner core collapses at a speed proportional to its distance from the center. Material near the center barely moves. Material farther out moves faster, and the whole structure maintains its density profile during the fall. It collapses in on itself like a balloon deflating uniformly, preserving its internal structure even as it shrinks. Why does the inner core collapse this way? Because information can still travel across it. The speed of sound inside the inner core is still faster than the speed at which the collapse is proceeding. Sound waves can cross the inner core in less time than the collapse takes. This means different parts of the inner core can still communicate with each other. They can still adjust to what the rest of the core is doing. They collapse together in coordinated fashion as a single object. The outer core, everything above that inner 6/10 of a solar mass, behaves completely differently. Out here, the collapse is happening so fast that the speed of sound cannot keep up. Information cannot travel across the outer core quickly enough for it to respond coherently. The outer core is falling supersonically. Different parts of the outer core have no idea what the other parts are doing. They are just falling, independently, chaotically, each region responding only to the gravity it feels locally. The outer core is like a waterfall. Everything is pouring inward, but there is no coordination, no structure, no coherence. It is pure free fall. The boundary between the inner and outer core, the point where the collapse speed equals the local speed of sound, is called the sonic point. This boundary will become extremely important later because it is essentially the dividing line between the region that will participate in the bounce and the region that will not. But we're getting ahead of ourselves. For now, the important thing is that the core is collapsing in two fundamentally different ways depending on which region you are looking at. The inner core falls as a unit. The outer core falls as a rain of independent material pouring inward at supersonic speed. Throughout this entire collapse, neutrinos continue to pour out of the core in astonishing quantities. The electron capture reactions that are driving the collapse are producing neutrinos at a rate that is almost impossible to comprehend. In the span of a few hundred milliseconds, the collapsing core will produce more neutrinos than the Sun will generate in its entire lifetime. The total energy carried by these neutrinos is staggering, roughly 3 times 10 to the 46 joules. That is roughly 250 times more energy than the Sun will radiate in 10 billion years of steady shining, and almost all of it is released in less than a second. At first, during the early stages of the collapse, the neutrinos escape freely. The core, despite being incredibly dense by ordinary standards, is still transparent to neutrinos. They are produced in the collapsing material, and they stream outward at nearly the speed of light, passing through the outer layers of the star and disappearing into space without interacting with anything. Even the dense stellar interior cannot stop these ghostly particles. They leave the star as if it were not there. But as the collapse progresses and the density climbs higher and higher, something remarkable begins to happen. Something that would seem impossible based on what we know about neutrinos under normal conditions. The core becomes opaque to neutrinos. This is extraordinary. Under normal circumstances, neutrinos pass through matter as if it did not exist. Trillions of them pass through your body every second without touching you. To detect even a single neutrino under normal conditions requires enormous underground detectors containing thousands of tons of material, carefully shielded from every other kind of particle. Even with all of that effort, those detectors might catch only a handful per day from the entire output of the Sun. But the density inside the collapsing core is not normal. As the collapse proceeds, the density surges past 100 billion times the density of water, climbing toward 1 trillion times. At these densities, the distance a neutrino could travel before interacting with something, what physicists call the mean free path, becomes shorter than the size of the core itself. The neutrinos are still moving at nearly the speed of light, but they keep bumping into things. They scatter off the incredibly dense matter, being deflected and redirected, unable to travel in a straight line for any significant distance. Think about what this means. Particles so ghostly that they can normally pass through a planet without noticing it are now trapped. The core has become so dense that even neutrinos cannot escape. They are imprisoned inside the collapsing material, bouncing around, unable to get out. A surface forms, a boundary called the neutrinosphere, analogous to the photosphere of a normal star, the surface of last scattering for neutrinos. Inside the neutrinosphere, neutrinos are trapped, diffusing slowly through the impossibly dense material. Outside it, they can stream freely. But the neutrinosphere is deep inside the core, and the neutrinos produced below it are stuck. This trapping has profound consequences. Remember, the neutrinos were carrying energy away from the core. They were one of the mechanisms by which the core was losing pressure support. But now that the neutrinos are trapped, they can no longer escape. Their energy is locked inside the core. This might sound like it would help to stabilize the core, and in a very minor way, it does add a small amount of pressure. But by this point, it is far too late. The collapse is proceeding too fast. The neutrino pressure is a tiny fraction of what would be needed to halt the infall. The core is past the point of no return. Trapping the neutrinos slows the energy loss, but it does not come close to providing enough support to stop what is happening. Let me pause here and ask you to absorb the speed of what we have just described. Everything I have just described, the initiation of electron capture, the onset of photodisintegration, the feedback loop between them, the acceleration of the collapse to a quarter of the speed of light, the separation into a coherent inner core and a supersonically falling outer core, the production of more neutrinos than the sun will emit in its entire lifetime, and the trapping of those neutrinos as the density exceeds 1 trillion times the density of water. All of this happens in roughly 300 milliseconds, about a third of a second. Less time than it takes to say the word collapse out loud. 300 milliseconds. That is the time scale. Remember the progression. Every stage of burning was shorter than the one before it, each one a fraction of the last, compressing the entire history of this star into an ever-tightening spiral. The final fuel lasted barely a day, and now the core that all of those reactions built, the iron core that represents the final product of millions of years of nuclear evolution, is destroyed in 300 milliseconds. Compare this to something familiar. A human blink takes about 300 to 400 milliseconds. The collapse of the core happens in roughly the time it takes you to blink once. In that single blink, a mass greater than our entire sun falls from the size of Earth to the size of a city. Temperatures surge past 100 billion degrees. Densities reach levels found nowhere else in the present-day universe outside of neutron stars and black holes. And more energy is released in neutrinos than the sun will produce across its entire 10 billion year lifespan. There is no gentle way to say this. What is happening inside this star is the most violent event that occurs in the universe outside of the Big Bang itself, and the mergers of compact objects like neutron stars and black holes. And it is happening in total silence, in total darkness, completely hidden from the outside universe. The surface of the star still looks normal. No light has escaped the core to signal what is happening. No gravitational wave has propagated outward yet. The star's photosphere, the visible surface that any telescope would see, is completely oblivious. It is still shining steadily, radiating the same light it has been radiating for millions of years, reflecting conditions that existed in the core hours or days ago. The surface is living in the past. The present is a catastrophe buried underneath trillions of tons of star. But the collapse is not going to last forever. The core cannot keep falling indefinitely. Something is waiting at the bottom. Something that will stop the collapse with a violence that matches the violence of the fall itself. Because as the inner core is squeezed smaller and smaller, approaching a diameter of just a few tens of kilometers, the density is climbing toward a threshold that will change everything. That threshold is nuclear density, the density of matter inside an atomic nucleus. Under normal conditions, nuclei are separated by vast empty spaces. Atoms are mostly empty. The nucleus occupies a tiny fraction of the atom's volume, but in the collapsing core, those empty spaces are being crushed out of existence. The nuclei are being forced closer and closer together, and when they finally touch, when the distance between nuclei drops to zero and the entire core becomes a single continuous mass of nuclear matter, a new force will enter the picture. A force that even gravity cannot easily overcome. The strong nuclear force, the same force that holds protons and neutrons together inside atomic nuclei, will suddenly resist further compression. The core will stiffen. The inner core, which has been falling as a coherent unit, will hit a wall of nuclear repulsion and rebound. It will bounce, and in that bounce, in that instant when the innermost core snaps back outward against the still falling material above it, a shock wave will be born. A shock wave that carries the potential to tear the entire star apart. But whether that shock wave actually succeeds in destroying the star is not a simple question. Because the shock wave faces its own set of devastating challenges. Challenges that will drain its energy, slow its progress, and threaten to kill the explosion before it ever reaches the surface. The core is about to hit bottom, and what happens at the bottom will determine whether this star becomes a supernova or simply disappears into a black hole without a trace. The inner core has been falling for roughly 300 milliseconds. In that fraction of a second, it has collapsed from a region the size of Earth to a ball perhaps 50 kilometers across and still shrinking. It is falling inward at roughly a quarter of the speed of light. The density at the center has already surpassed anything found on Earth, anything found in a white dwarf, anything found anywhere in the modern universe except inside neutron stars and black holes. And it is still climbing. But now the density crosses a threshold that changes everything. The core reaches nuclear density. This is the density of matter inside an atomic nucleus, roughly 230 trillion times the density of water. At this density, atomic nuclei are no longer separated by space. They are touching. They have been forced so close together that the individual protons and neutrons from neighboring nuclei are essentially in contact with one another. The entire inner core, a mass greater than our Sun, has been compressed into a single continuous sphere of nuclear matter. Not atoms, not nuclei with space between them. A single, incomprehensibly dense ball of neutrons and protons, roughly 30 to 40 kilometers across. And here, at this density, something new happens. Something that gravity has never had to contend with in the life of this star. The strong nuclear force, the most powerful force in nature at short range, stands up and pushes back. To understand what happens, you need to understand something about the strong nuclear force and how it behaves at very short distances. The strong force is what holds protons and neutrons together inside atomic nuclei. It is enormously powerful, roughly 100 times stronger than the electromagnetic force at nuclear distances. Without it, no nucleus heavier than hydrogen could exist. Protons repel each other electrically because they are all positively charged. But the strong force overcomes that repulsion and binds them together. However, the strong force has a very particular character. At the distances typically found inside a nucleus, about 1 femtometer, the force is intensely attractive. It pulls nucleons together with tremendous strength, but at distances significantly shorter than this, the force becomes repulsive. Ferociously repulsive. If you try to push 2 nucleons closer together than their natural separation, the strong force resists with a rigidity that is almost impossible to overcome. Nuclear matter, at the densities found inside atomic nuclei, is nearly incompressible. You can push it, you can squeeze it, but once you reach nuclear density, the material pushes back with a force that rivals gravity itself. This is what happens in the collapsing core. The inner core, that roughly 6/10 of a solar mass that has been falling inward as a coherent unit, slams into this wall of nuclear incompressibility. For 300 milliseconds, the inner core has been in free fall, accelerating under its own gravity, building up speed, gaining kinetic energy with every millisecond. And now, in an instant, it hits the bottom. The nuclear matter at the center stiffens. The equation of state, the relationship between pressure and density, suddenly changes. Where before the material offered little resistance to compression, it now offers enormous resistance. The core effectively becomes as rigid as a solid wall made of nuclear matter. And just like any object that slams into a rigid surface at high speed, the inner core bounces. This is core bounce. It is one of the most dramatic physical events that occurs in nature. The inner core, which has been contracting for a third of a second, suddenly reverses direction. The rebound is not gentle. It is violent, abrupt, and almost instantaneous. The innermost material, having been compressed slightly beyond nuclear density by its own momentum, springs back outward like a compressed spring being released. The timescale of the bounce itself is measured in milliseconds. In roughly a single millisecond, the inner core goes from still contracting to actively expanding. The density at the very center briefly exceeds equilibrium nuclear density, perhaps reaching 2 to 3 times nuclear density, before the repulsive component of the strong force drives the material back outward. Now consider what is happening at the boundary between this rebounding inner core and the material above it. The inner core is bouncing back. It is pushing outward. But the outer core, everything above the inner core, is still falling inward. It did not get the message. It is still collapsing at supersonic speeds, raining down on the inner core in a continuous avalanche of matter. The outer core has no way of knowing that the inner core has bounced because the information about the bounce cannot travel outward faster than the speed of sound. And the outer core is falling faster than sound can travel through it. The outer core is still in free fall, still pouring inward, completely oblivious to what has just happened below. So you have two masses of material moving in opposite directions. The inner core is pushing outward. The outer core is falling inward. They meet at the boundary between them. And when they collide, when the rebounding inner core crashes into the still falling outer material, the result is a shock wave. A shock wave is a sudden, violent discontinuity in pressure, density, and temperature. It is a wall of compressed material propagating outward through the star. Think of it like a sonic boom, but incomparably more powerful. On one side of the shock, the material is falling inward at tens of thousands of kilometers per second. On the other side, the material has been stopped, heated, and compressed by the collision. The transition between these two states happens across a distance of just a few kilometers. The shock is a knife edge, a boundary between ordered infall and violent disruption. This shock wave forms at the boundary of the inner core, roughly 40 to 60 kilometers from the center. At the moment of its birth, the shock is extraordinarily powerful. The temperatures immediately behind the shock front reach tens of billions of degrees. The pressure is beyond anything else in the current universe outside the cores of other collapsing stars and the interiors of neutron stars. The shock begins to move outward, pushing through the still falling outer core material like a plow through heavy snow. Here is where you might reasonably expect the story to end happily. You might think the shockwave simply blasts its way through the entire star, tearing it apart and creating the supernova we see from Earth. A clean, straightforward process. The core collapses, bounces, and the bounce produces a shock that explodes the star. Simple, elegant, done. That is exactly what astronomers originally thought happened. For decades, the leading model of core collapse supernovae was the prompt shock mechanism. The idea was that the shock wave generated by core bounce carries enough energy to push all the way through the outer core and into the star's envelope, ejecting the outer layers in a spectacular explosion. No additional physics needed. The bounce does it all, but it does not work. And understanding why it does not work is essential to understanding what actually happens in a core collapse supernova. The shock wave is born with an enormous amount of energy, perhaps 5 times 10 to the 44 joules. That is more energy than the sun will radiate in roughly 4,000 years of steady shining. In absolute terms, it is a staggering amount of energy. But the shock has to travel through the outer core, and the outer core is not empty space. It is filled with iron nuclei, falling inward at tens of thousands of kilometers per second. And as the shock plows through this material, 2 devastating processes drain its energy with merciless efficiency. The first energy drain is familiar. It is photodisintegration, the same process that helped trigger the collapse in the first place. Remember, photodisintegration is the breaking apart of iron nuclei by extremely energetic photons. When the shock wave passes through a region of the outer core, it heats the material to extreme temperatures. Those temperatures produce gamma-ray photons energetic enough to shatter iron nuclei into helium nuclei and free neutrons. Every iron nucleus that gets torn apart absorbs a tremendous amount of energy from the shock. It takes roughly 124 million electron volts of energy to break apart a single iron 56 nucleus. That might not sound like much, but the outer core contains an unfathomable number of iron nuclei. Every gram of material the shock passes through contains trillions upon trillions of them. And every single one that gets photodisintegrated steals energy from the shock. The numbers are devastating. For every 1/10 of a solar mass of iron-rich material the shock traverses, photodisintegration absorbs roughly 1.5 times 10 to the 51 ergs of energy. The shock has to plow through several tenths of a solar mass of this material. By the time it has crossed even a small fraction of the outer core, photodisintegration has consumed a catastrophic amount of its energy. The shock is being eaten alive. Every kilometer it advances costs it energy. It is like trying to drive a truck through a wall that gets thicker the farther you push. The second energy drain comes from neutrinos. Behind the shock front, the material is incredibly hot and dense. Under these conditions, neutrino-producing reactions proceed at enormous rates. Electron captures continue. Thermal processes produce neutrino pairs. And these neutrinos, at least in the region just behind the shock, where the density is not quite high enough to trap them, stream outward and escape the core entirely. Every neutrino that escapes carries energy with it. Energy that the shock cannot get back. The neutrinos are hemorrhaging energy from the region immediately behind the shock, further sapping its strength. These two processes working together are devastatingly effective. Within roughly 10 to 20 milliseconds after the shock is born, it has lost most of its energy. The shock that started with enough power to potentially unbind the star has been bled dry by photodisintegration and neutrino losses. It has pushed outward to a radius of roughly 100 to 200 kilometers from the center. And there it slows. It weakens. And it stalls. The shock does not disappear. It does not collapse back inward. It simply stops advancing. It becomes what physicists call a standing accretion shock, hovering at a radius of roughly 150 to 200 kilometers, suspended between the outward pressure behind it and the inward push of material still raining down. Material from the outer core continues to fall inward, passes through the shock, and settles onto the growing mass at the center. The shock is stuck. Behind the stalled shock, at the very center, something remarkable has formed. The inner core, that rebounding mass of nuclear density matter, has settled into a new equilibrium. It is a proto-neutron star. It is not yet a fully formed neutron star. It is still incredibly hot, still contracting slowly, still radiating enormous quantities of neutrinos from its surface. But it is a recognizable object. A ball of nuclear matter roughly 30 to 40 kilometers in diameter, containing more than a solar mass of material, held up by the degeneracy pressure of neutrons, and the repulsive core of the strong nuclear force. The temperature at its center exceeds 100 billion degrees. The density is several times nuclear density. It is the densest object in the visible universe outside of a black hole. The proto-neutron star is radiating neutrinos at a prodigious rate. These neutrinos are produced by the immense heat trapped inside it, and by ongoing nuclear reactions in its interior. The total neutrino luminosity, the rate at which the proto-neutron star is emitting energy in the form of neutrinos, is almost incomprehensible. In the first few seconds after core bounce, the proto-neutron star radiates roughly 3 times 10 to the 46 joules of energy entirely in neutrinos. We encountered this number during the collapse itself, but now all that energy is pouring out of a single compact object barely 40 kilometers across. For a few brief seconds, the neutrino luminosity of this one dying core exceeds the combined light of every star in the Milky Way by a factor of billions. All of it in the form of particles that, under any other circumstance, would pass through a planet as though it were empty space. This is one of the most astonishing facts in all of astrophysics. When a massive star collapses, the overwhelming majority of the gravitational energy released, roughly 99% of it, comes out as neutrinos, not as light, not as the spectacular visible explosion that we see from Earth. The visible supernova, as dramatic as it looks, carries only about 1% of the total energy. The neutrinos carry the rest. The real supernova, if you measure it by energy, is invisible to human eyes. It is a neutrino event, not a light event. But we're getting ahead of ourselves. Right now, the shock is stalled. The proto-neutron star is sitting at the center, radiating neutrinos. Material from the outer core was still raining inward, passing through the stalled shock and accreting onto the proto-neutron star. And the critical question, the question that defines the entire field of core collapse supernova theory, is this: will the shock be revived, or is this the end? Because if the shock is not revived, if nothing re-energizes it and pushes it outward, then there will be no supernova. The outer layers of the star will never be ejected. The material will continue to fall inward, piling onto the proto-neutron star. The proto-neutron star will gain mass, and if it gains enough mass, it will exceed the maximum mass that neutron degeneracy pressure and the strong force can support. At that point, the proto-neutron star itself will collapse. It will be crushed beyond nuclear density, beyond any force's ability to resist, into a black hole. The star will simply vanish. It will disappear from the universe without a visible explosion, without scattering its elements into space, without producing the expanding cloud of debris that we see in supernova remnants. It will just be gone. A black hole where a star used to be. This is not a theoretical abstraction. Astronomers believe that some massive stars do exactly this. They call them failed supernovae. The core collapses, the shock forms and stalls, and the shock is never revived. The star implodes, a black hole forms, and from the outside, the star simply fades away. There might be a brief, faint brightening as the outer envelope falls inward and releases some gravitational energy, but there is no dramatic explosion, no spectacular light show, no heavy elements scattered into the interstellar medium, just a quiet disappearance. In 2009, astronomers monitoring a survey of nearby galaxies noticed a red supergiant star called N6946-BH1 in the galaxy, NGC 6946. They had been watching it as part of a survey looking for supernovae. But instead of exploding, the star simply vanished. It faded away over a period of months and was gone. Follow-up observations with the Hubble Space Telescope confirmed that the star had disappeared without producing a luminous supernova. The most likely explanation is that the star's core collapsed directly into a black hole without a successful explosion. It was a failed supernova, a star that died in silence. This raises a genuinely unsettling possibility. If the shock stalls and is not revived, the star produces no supernova, no explosion, no ejection of heavy elements, no remnant visible to telescopes across the galaxy. The star simply ceases to exist as a visible object. And this means that the boundary between a successful supernova and a complete failure, between a spectacular cosmic explosion and a quiet cosmic disappearance, depends entirely on what happens to the stalled shock in the seconds after core bounce. Let us examine the situation more carefully. The shock is stalled at roughly 150 to 200 kilometers. Below the shock, material is falling inward and accreting onto the proto-neutron star. Above the shock, more material from the outer core and the lower layers of the star's envelope is raining down. The shock is being squeezed from both sides. It is losing energy through neutrino emission and gaining energy from the neutrino flux rising from the proto-neutron star below. But at this point, the gains are not enough to offset the losses. The shock is in a precarious balance, and without additional help, it will eventually fail. The proto-neutron star below the shock is extraordinarily luminous in neutrinos. It is radiating roughly 10 to the 53 ergs per second in neutrino energy during the first second after bounce. These neutrinos stream outward through the material between the proto-neutron star and the stalled shock. Most of them pass straight through without interacting, because neutrinos interact so weakly with matter. But a small fraction, a tiny percentage of them, do interact. They deposit energy into the material. And this energy deposition, small as it is compared to the total neutrino flux, might be enough to make the difference. But we are not there yet. Right now, in this moment, the shock is stalled. The proto-neutron star is forming. The outer material is still falling. And the fate of the star hangs in the balance. The next few 100 milliseconds will determine everything. Will the shock be revived and blast the star apart, or will the star collapse silently into a black hole? Consider the brutality of the timescale. The core bounce happened. The shock formed. And within roughly 10 to 20 milliseconds, less time than a single frame of a movie displayed on screen, the shock has already stalled. In less time than it takes you to blink, the most powerful shockwave in the known universe has been stopped dead in its tracks by the sheer energy cost of plowing through iron-rich material and by the relentless drainage of neutrino emission. The shock traveled only about 150 kilometers before exhausting itself. 150 kilometers. In a star that is hundreds of millions of kilometers across. The shock made it a tiny fraction of a percent of the way through the star before it ran out of energy. Think about the contrast. The star is millions of kilometers across. The entire drama of the core collapse, the bounce and the shock formation played out within a region roughly 30 to 60 kilometers in radius. The stalled shock sits at about 150 to 200 kilometers. Everything we have described, the most violent events in the universe, is taking place in a volume smaller than many cities on Earth. If you could somehow look down at the star from above, you would see a sphere millions of kilometers wide looking completely undisturbed, with a region smaller than a large metropolitan area at its absolute center, where the laws of physics are being tested to their limits. And even within this tiny central region, there are zones. There is the proto-neutron star at the very center, a ball of nuclear matter a few tens of kilometers across, incredibly hot, incredibly dense, radiating neutrinos at an almost unbelievable rate. There is the region between the proto-neutron star surface and the stalled shock, filled with falling material that is being heated by neutrinos from below and cooled by neutrino emission of its own. And there is the shock itself, that standing discontinuity where infalling material slams into the wall of heated, pressurized gas behind the shock front and is suddenly decelerated, heated, and compressed. This middle region, between the proto-neutron star surface and the stalled shock, is where the battle for the supernova will be fought. It is a zone of extraordinary complexity. Material falls inward while neutrinos stream outward. Some neutrinos are absorbed, depositing energy. Some energy is radiated away as new neutrinos. Temperatures range from tens of billions of degrees near the proto-neutron star surface to a few billion degrees near the shock. Densities span several orders of magnitude, and the entire structure is changing on timescales of milliseconds. Within this region, there is a critical boundary. Below a certain radius, the neutrinos streaming up from the proto-neutron star are actually losing energy to the material. They are being absorbed, but the material is so hot and dense that it radiates neutrinos of its own even faster than it absorbs them. There is a net loss of energy from the material. This region is called the cooling layer. It loses energy and sinks inward, settling onto the proto-neutron star. Above this boundary, something different happens. Here, the material is less dense and slightly cooler. The neutrinos streaming up from below are absorbed, and the energy deposited by these neutrinos exceeds the energy lost through the material's own neutrino emission. There is a net gain of energy. This region is called the gain region, and it is perhaps the most important zone in the entire collapsing star, because the gain region is where the energy that might revive the shock is being deposited. The gain region is a relatively thin shell, perhaps a few tens of kilometers thick, located between roughly 60 and 150 kilometers from the center. It sits just below the stalled shock. Neutrinos from the proto-neutron star pass through this region, and a small fraction of them are absorbed, heating the material. If enough energy is deposited in the gain region, the pressure behind the shock will increase. If the pressure increases enough, the shock might start moving outward again. If the shock moves outward, more material enters the gain region, absorbing more neutrinos, adding more pressure, pushing the shock further. This is the neutrino-driven mechanism. It is the leading theoretical framework for understanding how core collapse supernovae actually explode. The idea is that the neutrinos from the proto-neutron star, despite being almost impossibly difficult to stop, deposit just enough energy in the gain region to revive the stalled shock and drive a successful explosion. But notice the word might. Notice the uncertainty. Because whether or not the neutrino-driven mechanism actually works depends on a knife-edge balance between energy gains and energy losses in the gain region. The neutrinos deposit energy, but much of that energy is immediately radiated away by neutrino emission from the heated material itself. The net energy available to revive the shock is only a small fraction of the total neutrino luminosity. If the neutrino luminosity from the proto-neutron star is high enough, if the gain region is large enough, if the material spends enough time in the gain region to absorb enough neutrinos, then the shock might be revived. But if any of these conditions fall short, the shock will remain stalled. Material will continue to accrete onto the proto-neutron star. The proto-neutron star will gain mass, and eventually it will collapse into a black hole. The situation is genuinely on a knife edge. Whether the neutrino heating can overcome the energy losses depends on a delicate balance that the gain region alone may not be able to tip. The neutrinos are depositing energy, but much of it is immediately radiated away. The net gain is slim, and slim may not be enough. If this were the whole story, if the physics of the collapsing core were perfectly spherical and perfectly smooth, the shock might never revive at all. The neutrino heating would fall just short. The shock would remain stalled. Material would keep accreting, and eventually, the proto-neutron star would collapse into a black hole. A star that dies without an explosion, without scattering its elements, without producing the iron in your blood, the calcium in your bones, the oxygen you are breathing right now. If the spherical picture were the whole truth, you would not exist, and yet you do, which means the spherical picture is missing something. Something that changes the outcome. Something that takes a mechanism that almost works and pushes it over the edge. That something lives in the messy, violent, three-dimensional reality of fluid motion behind the stalled shock. It involves instabilities that reshape the shock from a sphere into something lumpy and asymmetric. It involves convective plumes that carry energy from the gain region up to the shock front. And it involves a global oscillation of the shock itself that might be the final push needed to turn a stalled shock into a successful supernova. The proto-neutron star is radiating. The stalled shock is hovering. Material is still falling. And somewhere in the thin shell of the gain region, the seeds of an explosion might be taking root. The question is whether those seeds will grow fast enough, or whether gravity will win and the star will collapse into darkness. The clock is still ticking. And the next few hundred milliseconds will decide everything. The shock is stalled. It has been sitting at roughly 150 to 200 kilometers from the center for milliseconds that feel like eternities in the compressed timescales of a collapsing core. Below it, the proto-neutron star is radiating neutrinos at a luminosity that defies comprehension. Above it, the outer core is still raining inward, feeding mass through the shock and onto the growing proto-neutron star. The clock is ticking. If the shock is not revived soon, the proto-neutron star will gain too much mass and collapse into a black hole. The star will die in silence, No explosion, no supernova, no scattering of heavy elements into the galaxy. But we arrived at the edge of something important. The gain region. That thin shell of material sitting just below the stalled shock, where neutrinos from the proto-neutron star are depositing more energy than the material is radiating away. This region is the battlefield, and it is here that the explosion will either succeed or fail. The neutrino-driven mechanism works like this. The proto-neutron star, that newly formed ball of nuclear matter at the center, is extraordinarily hot and luminous. It is cooling itself by radiating neutrinos in every direction. These neutrinos stream outward through the material above the proto-neutron star. Most of them pass straight through without interacting, because neutrinos interact with matter so weakly. But in the gain region, where conditions are just right, a small fraction of the neutrinos are absorbed. Each absorbed neutrino deposits its energy into the material. This heats the gas. Hotter gas has higher pressure. Higher pressure pushes outward against the stalled shock. The fraction of neutrinos that gets absorbed is tiny. Perhaps 5 to 10% of the neutrino flux passing through the gain region is captured. That does not sound like much, but remember the total neutrino luminosity. The proto-neutron star is radiating roughly 3 times 10 to the 46 joules of energy in neutrinos over a few seconds. Even 5% of that is an enormous amount of energy. The question is whether it is enough, deposited in the right place at the right time, to push the shock outward against the relentless infall of material from above. In a perfectly spherical, one-dimensional model, the answer is usually no. The heating is not quite sufficient. The shock absorbs energy from neutrinos below, but it also loses energy as the heated material emits its own neutrinos. The balance between heating and cooling is too close. The shock sits there, stuck, unable to advance, slowly losing ground as more and more material piles on from above. This is what made the supernova problem so frustrating for decades. The mechanism seemed right in principle but failed in practice. The neutrinos were there, the energy was there, but somehow it was not enough. The breakthrough came when physicists stopped assuming the star was a perfect sphere. Because real stars are not perfect spheres. Real collapses are not perfectly symmetric. And when you allow the material behind the stalled shock to move in more than one dimension, something dramatic happens. Fluid instabilities develop. Convective plumes form. Turbulence erupts. And these multidimensional motions change everything. Let me explain convection first because it is familiar. You have seen convection in your kitchen. When you heat a pot of water on a stove, the water at the bottom gets hot first. Hot water is less dense than cold water, so it rises. Cooler water from the top sinks to replace it. This creates a circulation pattern, hot material rising, cool material sinking, that efficiently transports heat from the bottom of the pot to the top. This is convection. It is one of the most fundamental processes in fluid dynamics, and it happens wherever you have a fluid heated from below and cooled from above. The gain region behind the stalled shock is heated from below by neutrinos from the proto-neutron star, and effectively cooled from above by the energy losses at and near the shock front. This is exactly the configuration that drives convection. Hot material near the bottom of the gain region rises. Cooler material near the shock sinks. Convective plumes develop, carrying hot, energized material upward toward the shock and bringing cooler material downward where it can absorb more neutrino energy. This convective overturn does something critically important. It increases the amount of time that material spends in the gain region. In a one-dimensional model, material falls straight through the gain region. It enters from above, absorbs some neutrino energy on its way down, and settles onto the proto-neutron star. The time it spends in the gain region, the time it has to absorb neutrinos, is limited by how fast it falls through. But with convection, material circulates. It rises, falls, rises again. It gets recycled through the gain region multiple times, absorbing more neutrino energy with each pass. The effective residence time in the gain region increases dramatically, and more time in the gain region means more energy absorbed. Convection also transports energy more efficiently. Instead of relying on slow thermal diffusion to carry heat from the gain region to the shock, convective plumes physically carry hot material upward and deposit it directly behind the shock front. This is far more efficient. It delivers energy where it is needed, right behind the shock, increasing the pressure there and helping to push the shock outward. But convection alone may not be sufficient. There is another instability that may play an equally important role, and it operates on a completely different scale. It is called the standing accretion shock instability, or SASI for short, and it is one of the most remarkable fluid dynamical phenomena in all of astrophysics. SASI is a global oscillation of the stalled shock itself. Instead of remaining a perfectly spherical surface, the shock begins to wobble. It deforms. One side of the shock pushes outward while the opposite side pushes inward. The shock sloshes back and forth, developing a large-scale asymmetric motion that grows over time. The mechanism behind SASI involves an interplay between the shock, the material flowing through it, and acoustic and vorticity waves that bounce between the shock and the surface of the proto-neutron star. Perturbations at the shock create disturbances that travel inward, reflect off the proto-neutron star, and travel back outward to the shock, amplifying the original perturbation. It is a feedback cycle that amplifies asymmetry with each oscillation. The period of SASI oscillations is measured in milliseconds. The shock wobbles back and forth on timescales of roughly 10 to 30 milliseconds, depending on the conditions. With each oscillation, the asymmetry grows. The shock becomes increasingly deformed, and this deformation has a profound effect on the dynamics. When the shock bulges outward on one side, the gain region on that side becomes larger. Material in the expanded gain region spends more time being heated by neutrinos. It absorbs more energy. The pressure behind the shock on that side increases, pushing the shock outward even further. Meanwhile, on the opposite side, where the shock has retreated inward, material falls more directly onto the proto-neutron star, feeding its luminosity and maintaining the neutrino flux. SASI effectively creates a configuration where energy is being concentrated and directed rather than spread uniformly over a sphere. The combination of convection and SASI working together creates a violently turbulent, highly asymmetric environment behind the stalled shock. Hot plumes of neutrino-heated material rise and slam into the shock from below. The shock wobbles and deforms, sometimes dramatically. Eddies and vortices form, break apart, and reform. The entire region between the proto-neutron star and the shock is a churning, chaotic mess of hot gas being heated, stirred, and pressurized. And this is the key. In many modern three-dimensional simulations, this combination of neutrino heating, convective overturn, and SASI is enough to revive the shock. Not in every simulation, not for every stellar mass, and not in the same way each time. But in a significant number of cases, the shock begins to move outward again, slowly at first, pushed by the accumulated pressure of neutrino-heated material and aided by the turbulent motions that channel energy where it is needed. The shock accelerates, it gains ground, and eventually it reaches escape velocity, pushing outward faster than new material can fall inward. The explosion has begun. But notice something about this process. It is inherently asymmetric. The convective plumes, the Sayce oscillations, the turbulent eddies, none of these are spherically symmetric. They break the symmetry of the problem in dramatic and unpredictable ways. The shock does not re-expand as a perfect sphere. It pushes outward more strongly in some directions than others. The explosion is lopsided. This asymmetry is not a minor detail. It is a fundamental prediction of modern supernova theory. Core collapse supernovae are not clean, symmetric explosions. They are messy, turbulent, asymmetric events. The shock pushes outward unevenly. Some material is ejected at higher velocities in some directions than others. The newly formed neutron star can receive a gravitational kick from the asymmetric ejection of material, and this kick can send it flying through space at hundreds of kilometers per second. Many observed neutron stars have very high velocities relative to their surroundings, and this is believed to be a direct result of the asymmetric explosion that created them. We also see direct evidence of asymmetry in supernova remnants. When astronomers image the expanding debris clouds left behind by ancient supernovae, they find material distributed unevenly, with jets and lobes and clumps scattered in seemingly random directions. This is exactly what you would expect from an explosion driven by turbulent, asymmetric processes rather than a clean, spherical blast. Now, I need to be honest about something. Despite enormous progress over the past 2 decades, the supernova explosion mechanism is not fully understood. Modern 3-dimensional simulations are incredibly sophisticated. They solve the equations of fluid dynamics, neutrino transport, nuclear physics, and general relativity simultaneously on some of the most powerful supercomputers in the world. A single simulation of the first few seconds after core bounce can take months of computing time, even on machines capable of performing quadrillions of calculations per second. And yet, these simulations do not always agree with each other. Different research groups using slightly different numerical methods, slightly different treatments of neutrino physics, or slightly different initial stellar models can get different results. Some simulations explode robustly, others struggle. Some produce explosions that are too weak compared to what we observe in real supernovae. Others produce explosions that are too energetic. The details remain uncertain. What is generally agreed upon is the broad framework. Core collapse produces a bounce and a shock. The shock stalls. Neutrino heating in the gain region, aided by convection and Sayce, provides the additional energy needed to revive the shock in many cases. The resulting explosion is asymmetric, but the precise conditions that determine whether a given star explodes or fails, whether it leaves behind a neutron star or a black hole, how much energy the explosion carries, and how the heavy elements are distributed in the ejected material, these details are still being worked out. Not every massive star produces the same outcome. Stars at the lower end of the mass range for core collapse, perhaps 8 to 12 solar masses, may produce relatively weak explosions and leave behind low-mass neutron stars. Stars at higher masses may produce more energetic explosions, or they may fail entirely and form black holes. The relationship between the initial mass of the star and the outcome of the collapse is not a simple one. It depends on the structure of the star at the moment of collapse, the composition of its core and envelope, its rotation rate, and possibly its magnetic field. Two stars with similar initial masses but different internal structures might produce very different outcomes. The mapping from initial star to final fate is still an active area of research, and it may never be a simple formula. What we can say with confidence is that the core collapse process is real, that it happens in nature, and that it produces the supernova we observe. The evidence for this is overwhelming. We have observed supernova. We have studied their remnants. We have detected the heavy elements they produce scattered throughout the galaxy. And in one extraordinary case, we have detected the neutrinos. On the 23rd of February, 1987, a massive star in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, roughly 168,000 light-years away, exploded. This event, designated supernova 1987A, was the closest observed supernova since Kepler's supernova in 1604. It was visible to the naked eye from the southern hemisphere, and it was studied intensely by astronomers around the world. Supernova 1987. A provided the first, and so far only, direct confirmation that core collapse supernova produce neutrinos exactly as theory predicts. Here is what happened. Roughly 3 hours before the supernova was first seen in visible light, two neutrino detectors on Earth registered a sudden burst of neutrino detections. The Kamiokande 2 detector in Japan detected 11 neutrinos. The IMB detector in the United States detected 8. A third detector in Russia, the Baksan detector, detected an additional 5, though these detections were initially more ambiguous. The total was roughly 24 neutrinos, detected within a span of about 13 seconds. 24 neutrinos. That might not sound impressive, but consider what it means. The detectors were designed to detect solar neutrinos, which arrive in huge numbers because the Sun is relatively close. Supernova 1987A was 168,000 light-years away. The neutrinos from the supernova had been traveling for 168,000 years to reach Earth. They had crossed an entire dwarf galaxy and traversed the void between the Large Magellanic Cloud and the Milky Way. And despite the enormous distance, despite the fact that neutrinos interact with matter so weakly that most of them pass through the Earth without touching anything at all, roughly 24 were caught. The fact that any were detected is extraordinary, and the timing is crucial. The neutrinos arrived roughly 3 hours before the first visible light from the supernova. This makes perfect physical sense. The neutrinos are produced in the core during the collapse and in the first seconds after bounce. They escape the core within seconds, streaming outward at nearly the speed of light. They pass through the outer layers of the star as if those layers did not exist. Because neutrinos barely interact with ordinary matter, the neutrinos are free. They escape the star within seconds of the collapse, but the light cannot escape that quickly. The shock wave, revived by neutrino heating and turbulent convection, still has to travel through the rest of the star. The outer layers of the star extend for millions of kilometers. The shock, even moving at tens of thousands of kilometers per second, takes hours to reach the surface. Only when the shock breaks through the stellar surface does the star begin to brighten in visible light. The neutrinos, produced in the core and emitted immediately, arrive at Earth hours before the light that was produced when the shock finally reached the surface. This time difference, neutrinos first and light hours later, is a direct window into the physics of the collapse. The neutrinos tell us about the core, the light tells us about the surface, and the gap between them tells us how long it took the shock to traverse the star. Supernova, 1987. A confirmed what theorists have been predicting for decades. The core collapses first, the neutrinos come out first, the light comes later. Those roughly 24 neutrinos from 1987 also confirmed basic predictions about the energetics of core collapse. The energies of the detected neutrinos, the duration of the burst, and the total number detected were all broadly consistent with the theoretical expectation that roughly 3 × 10 to the 46 joules of energy is released in neutrinos during a core collapse. The observations match the theory. The neutrino-driven mechanism, or at least the broad framework of core collapse and neutrino emission, was confirmed by real data from a real supernova. Now imagine what we could learn from the next nearby supernova. The detectors that caught those 24 neutrinos in 1987 were small by modern standards. Today, we have far more powerful neutrino detectors. Super Kamiokande in Japan contains 50,000 tons of ultra-pure water and can detect neutrinos with much greater sensitivity. IceCube at the South Pole uses a cubic kilometer of Antarctic ice as a neutrino detector. Dune, currently under construction in the United States, will use 40,000 tons of liquid argon and will be particularly sensitive to the type of neutrinos produced in core collapse. If a star collapsed in our own galaxy, roughly 10 times closer than the Large Magellanic Cloud, these detectors would not catch 24 neutrinos. They would catch tens of thousands, possibly hundreds of thousands. With that many neutrinos, we could reconstruct the collapse in exquisite detail. We could measure the exact moment of core bounce by looking for a sharp spike in the neutrino signal. We could track the formation of the proto-neutron star by watching how the neutrino energies and luminosities change over the first few seconds. We could detect the onset of convection and seize through fluctuations in the neutrino signal caused by the turbulent motion of material near the neutrinosphere. We could determine whether a neutron star or a black hole formed by watching whether the neutrino signal cuts off abruptly, which would indicate the formation of a black hole swallowing the proto-neutron star, or fades gradually over tens of seconds, which would indicate a surviving neutron star cooling down. There is another messenger that could reach us even before the neutrinos arrive in meaningful numbers. Gravitational waves. Core bounce produces a sharp burst of gravitational radiation as the inner core suddenly decelerates and rebounds. The asymmetric motions driven by convection and seize produce a continuous, lower amplitude gravitational wave signal that lasts for hundreds of milliseconds after bounce. A rotating core could produce even stronger gravitational waves. Gravitational wave detectors like LIGO are already operating, and more sensitive detectors are being planned and built. If a core collapse occurred within our galaxy, LIGO would likely detect the gravitational wave signal from the bounce and from the turbulent post-bounce dynamics. Combined with the neutrino signal, this would give us 2 independent windows into the physics of the collapse, each probing different aspects of the process. The neutrinos tell us about the thermal state and composition of the core. The gravitational waves tell us about the bulk motion of matter, the asymmetries, the rotation. the violence of the bounce itself. Together, neutrinos and gravitational waves would allow us to watch a core collapse unfold in something approaching real time, even though the visible light from the supernova would not arrive for hours or even days. We would know that a star had collapsed, we would know what was happening at its center, and we would be watching, waiting, with our telescopes pointed in the right direction for the moment the shock wave finally breaks through the stellar surface and the sky lights up. That moment, the moment the shock reaches the surface, is called shock breakout. It is the transition point between everything we have discussed tonight and the supernova that the rest of the universe can see. For hours, the shock has been traveling through the star, plowing through the outer layers of hydrogen and helium, accelerating as it moves into less dense material. The material ahead of the shock has no idea what is coming. It is still the same calm stellar envelope that has existed for millions of years. And then the shock arrives. When the shock breaks through the photosphere, the visible surface of the star, an intense burst of ultraviolet and X-ray radiation is released. This shock breakout flash is brief, lasting perhaps minutes, but it is extraordinarily bright. It marks the first moment that electromagnetic radiation from the supernova escapes into space. Before this moment, all the information about the collapse was carried by neutrinos and gravitational waves. After this moment, light takes over, and the supernova becomes visible to telescopes and eventually to the naked eye. The shock breakout is followed by the expanding and brightening supernova, the spectacular display that can outshine an entire galaxy for weeks. But that display, as dramatic as it is, represents only about 1% of the total energy released in the collapse. The other 99% was carried away by neutrinos in those first few seconds, invisible to any telescope, detectable only by specialized underground detectors waiting patiently for particles that barely interact with matter. Let me bring this all the way back to where we started. Right now, somewhere in our galaxy, there is almost certainly a massive star with an iron core approaching instability. From the outside, it looks perfectly normal. Its light is steady, its color is unremarkable. There is no visible warning of any kind. But deep inside, silicon is burning, iron is accumulating, the core is growing heavier, the electrons are becoming more relativistic, the support is weakening, and at some point, perhaps tomorrow, perhaps in 1,000 years, perhaps in 100,000, the balance will fail. Electron capture and photodisintegration will trigger a runaway collapse. The inner core will fall to nuclear density in 1/3 of a second. It will bounce, a shock wave will form and stall. Neutrinos from the proto-neutron star will heat the gain region. Convection and instability will channel that energy toward the shock. And if the physics works out, if enough energy is deposited in the right place at the right time, the shock will be revived. The explosion will be asymmetric and violent. The neutron star left behind may be kicked to enormous velocity. Heavy elements forged in the explosion will be scattered into the interstellar medium, where they will eventually be incorporated into new stars, new planets, and perhaps new life. The iron in your blood, the calcium in your bones, the oxygen in every breath you take, all of it was produced in events exactly like this one, billions of years ago, in stars that no longer exist. We cannot predict exactly when the next galactic core collapse will happen, but we know it will happen. The Milky Way produces roughly 2 to 3 supernovae per century. Though most are hidden behind interstellar dust, and go undetected in visible light. The last supernova in our own galaxy visible to the naked eye was Kepler's supernova in 1604, over 400 years ago. We are statistically overdue. When it happens, the neutrinos will reach us first. Hours before the star visibly brightens, our underground detectors will register a sudden flood of neutrino events. Alerts will go out. Telescopes around the world and in space will swing toward the predicted location. And for the first time in human history, we will watch a supernova from the inside out, seeing the neutrinos from the core collapse, detecting the gravitational waves from the bounce, and then witnessing the shock break out as the star finally tears itself apart in visible light. Everything we've discussed tonight, the iron core sitting at the edge of stability, the twin catastrophes of electron capture and photodisintegration, the collapse to nuclear density in a third of a second, the core bounce, the stalled shock, the neutrino heating and turbulent convection that may revive it. All of this is hidden from the universe for hours. The most violent event a star can experience plays out in total silence, inside a shell of ordinary-looking stellar material that gives no outward sign of the apocalypse raging at its center. And then the shock arrives at the surface. The star brightens, a new light appears in the sky, and the universe can finally see what the core has been doing all along. That is the final second before a supernova. Not the whole explosion, not the weeks-long brightening that astronomers observe with their telescopes. Just the first second, the hidden second, the second when a stable iron core becomes an unstable iron core, when the floor drops out from under it, when it falls to nuclear density and bounces, when a shock forms and stalls, and when, if the physics is kind, that shock is revived by the faintest of particles, depositing just enough energy in just the right place. 1 second. That is all it takes to decide whether a star scatters its elements across the galaxy or collapses silently into a black hole. 1 second to determine whether the atoms it forged over millions of years of nuclear burning will be recycled into new worlds or locked away forever behind an event horizon. 1 second that shapes the chemical evolution of the galaxy and makes possible the existence of planets, oceans, atmospheres, and life itself. You exist because this process worked. Somewhere, billions of years ago, in a star that no longer exists, the shock was revived, the explosion succeeded, the heavy elements were scattered, and eventually across millions and billions of years, those elements drifted through interstellar space, collapsed into a new solar system, formed a rocky planet orbiting a modest yellow star, and through processes we still do not fully understand, organize themselves into living things. Everything you were made of was once inside a star that died in exactly this way. You are the product of a 1 second event that happened billions of years ago, in a star whose name you will never know, whose light has long since faded, whose remnant might still be out there as a neutron star spinning quietly in the dark. The next time you look up at the night sky and see a bright star in the constellation Orion or Scorpius or Cygnus, remember that somewhere inside it, or inside a star much like it, this process may already be underway. The surface may look calm, the light may seem steady, but deep inside, an iron core may be growing toward instability. And when it finally crosses the edge, when the last support gives way and the collapse begins, the universe will barely have time to notice before it is over. 1 second. That is all it takes, and that 1 second changes everything.